Three resistors. We have three resistors in a circuit, and we'd like to find the equivalent resistance of the circuit, the current from the battery, the current through this resistor here, R3, the current through R1, the voltage drop across R2, the power used by R3, so we're jumping around a bit here, and the amount of charge that flows through R1 in 2 minutes. Find the equivalent resistance for the circuit. So we first look at where something is perfectly in parallel or perfectly in series with another resistor. And what we have here is these two resistors are perfectly in series. Any current that goes through the first one has to go through the second one. It has no other choice. So we combine them to form an equivalent resistance, and our notation will be R sub 1, 2, indicating resistor 1, resistor 2. So that's not a 12, that's 1, 2. So since they're in series, we just add them. So R12, which will be the equivalent resistance of resistors 1 and 2, is 18 ohms. We redraw the circuit to show R12, which is taking the place of resistors 1 and 2, and will behave just like resistors 1 and 2 will. R12 does not physically exist. It's a virtual resistor. It's an equivalent resistance. We now see, hopefully, that it's in parallel with R3. So we have to use this equation to find the equivalent resistance of this combination. So we put in our values. We have 1/18 ohm plus 1/6. We look for least common denominator, which happens to be 18. So we have 1/18 plus 3/18. Add them together, 4/18, reduce it, 2/9 ohms. Now do not stop here. That's a somewhat common mistake. 1 over R equivalent equals that. We need R equivalent, so you flip it. You invert it. So R equivalent is 9 ohms divided by 2, and then you make it into a decimal, 4.5 ohms. We draw the final circuit analysis. We have one equivalent resistance here. Again, it's not a real resistor. It acts like the other three resistors, and it's 4.5 ohms. Different names for it. Net resistance, equivalent resistor. Any one of those will work. Find the current from the battery. Well, this was the point of finding the equivalent resistance. So we have a resistance and we have a voltage. We use Ohm's Law, and it is the battery voltage divided by the equivalent resistance of the circuit. So it's 9 divided by 4.5 ohms, and we get 2 amps. We could not find the current by dividing the battery voltage by either R1, R2, or R3. They need to be reduced to one equivalent resistance as shown. So we show the 2 amps going around the circuit, leaving the battery, going through the equivalent resistance, and coming on back to the battery. Let's go back to the original schematic. Right, that's just a fancy word for drawing, showing the physical resistors, adding the equivalent resistance and the current from the battery. And we put the equivalent resistance down here, and the current, we also could have written it down here, however you like. I is 2 amps. But because we had it flowing through the circuit, figured that would be enough so you know the current going through the battery. We need to find now the current through R3. Right here. We need the current there. It's not 2 amps. The current from the battery will split before the parallel resistance is, so it's going to go something like that. So not all the current is going to go through R3. So how do we find out what part of the current goes through R3? Well, first, let me just erase some of this, my lines there. What can we find out about R3 other than the resistance which is given? Well, this part of the resistor is connected to the positive terminal of the battery. The other part is connected to the negative, and there's no other resistors in between there. So whatever the voltage drop is across the battery or supplied by the battery, that has to be the voltage drop across R3. So we go ahead and write that in. R3 is in parallel with the battery, and there are no other resistors between R3 and the battery, so it has the same voltage drop as the voltage supplied by the battery. Now we can find the current through R3 by using Ohm's Law, right here. We just said the voltage was 9 volts. We know the resistance, so it's 9 volts divided by 6 ohms, and we have 1.5 amp going through the R3 resistor. It's very good that it's less than 2 amps or we would have had a problem. The current I equals 2 amps coming from the battery splits over here. We're going to label the current I sub 1, 2 as this current, the current going through resistors 1 and 2. Since they're in series, I12 is equal to the current going through R1 and also the current going through R2. They're in series. They will add to the current that's going through R3 to equal the current from the battery. Right? We've got the 2 amps here. 1.5 amps goes through here, so that means a half amp has to go through here. They'll recombine at the other end, so you have 0.5 plus 1.5 will equal 2 to get back to the battery. So a little more formal here. The total current from the battery, I, is equal to the current through the top leg of the parallel resistors plus I3, which is the current through the R3 or the bottom part of the parallel resistors. I12 is equal to I1, and we need to solve for I1. It will equal, we just rearrange the first equation, current coming from the battery minus the current going through resistor 3, 2 minus 1.5, and we get 0.5 amps. We now need the voltage drop across R2. And if you notice what we've been doing, we've been annotating the various circuit elements with what we find. So there was our equivalent. Here's the whole story about R3. We've added the currents up here. So now, when we need the voltage drop across R2, we already have the current in the resistance, and we just use Ohm's Law. And we find out that the voltage drop across R2 is 4 volts. Find the power used by R3. What's nice about annotating the different circuit elements is look at this. I have the whole story about R3 right here. So I can use any equation I want for power. We can do I squared R, V squared over R, IV. But since we were given R3 and V3 is equal to 9 volts, which we did without any calculations, we'll use V squared over R. So power is equal to V squared over R. All the subscripts are 3 because we're interested in resistor 3. And we get 13.5 watts. Now we need how much charge goes through R1 in 2 minutes. Well, we found the current up here. So we use a definition of current, which is the amount of charge divided by time. Rearrange that so we have the amount of charge is equal to I1 times T. Here's our current. We're told 2 minutes, but don't be tricked. Don't just multiply 2 times 0.5. We need it in seconds. So we have 60 seconds per minute, little unit conversion, and we find that 60 coulombs is the amount of charge that went through R1.